All right, guys, so we're going to go over our semester exam review here. Number one, which statement is true about the relation shown in the graph below? It is a function, or it is not a function. Appears how pretty much all four options begin. So remember, to check whether or not something is a function, we had what was called the vertical line test, which says if we draw a vertical line in anywhere, it should not pass through our function more than once. If it does, it is not a function. So in this case, this fails the vertical line test and is not a function because specifically for this x value, there are two different y's. There are multiple y values for a given x. So number one is C. Number two, which set of ordered pairs is not a function? Remember, to be a function, think about what we talked about earlier in the year. These are like x is kind of like our items, and y is kind of like their prices. We use the menu board, right, as an idea. So the same item can have, or different items can have the same price. That was okay. So say, for instance, something like this would be fine. These two items both have a price of $5 or whatever. However, the same item cannot have two different prices. That was not a function. So as we look through our table here, as we look at our x coordinates, the first thing I want to look for is, are there any repeated x's? And in fact, in number one, there are. And if we look at their corresponding y values, they are different. We have the same item with two different prices. So which one of these is not a function? A. The other ones are actually all functions. If you check the rest of them, none of the x values even repeat. So they're all different items. Does it matter that they're all the same price? Nope. I mean, think about the dollar store, right? Everything's a dollar in there. So every other set would still represent a function and would pass a vertical line test. For number three, let f of x equal the square root of x and g of x equal this. Describe g of x in terms of the parent function f of x. So as we look at these, it's talking about vertical shrinking or stretching, that's like compressing, and some translations. And this is in the form with a, h, and k. In fact, we just did this in our last chapter here. So if I identify from our equation here, a is 2. Positive means there's no vertical reflection, but the 2 does give me a vertical stretch. It's going to make my graph taller by a factor of 2. And remember that h and k represent our shifting. So h, which is the opposite of what it looks like in there, is positive 4, and that is a shift right 4 units. K, which is positive 6, is our vertical shift. And in this case, because it's positive, we are going up 6. So in fact, the only one that even had a vertical stretch, which was B, has the correct translation, right 4 and up 6. Number 3 is B. Number 4, if negative 3, 1 is in our function, which of the following points will be in the inverse of f of x? So remember, that's notation for inverse. And when you see the word inverse, we're talking about switching or swapping x and y. So if we swap x and y here, this has to be a point that will be on our inverse. So 4 is A. Number 5, again, it's talking about the inverse. So we're thinking about switching or swapping x and y. And so we're just going to immediately do that in our equation. Now, none of these equations match our current form. In fact, they all say y equals. So we're going to need to get y by itself. So let's move the term with x to the other side. So we now have 2y equals negative 3x plus 6. And divide everything by 2. And we have a choice. We could make this side one large fraction, which, looking at all my answers, it looks like that's not what the authors did of this question. Or we can make sure that each term, or all terms, are divided by 2. I think that's the option we're going to go with here. So we end up with negative 3 halves x, and 6 over 2 is 3. Negative 3 halves x plus 3. B is 5. Okay, number 6. The accompanying diagram represents the graph of f of x. which graph below represents the inverse of f of x? So again, that's notation for inverse. And you might remember that inverses reflect over the line y equals x, this diagonal line. So if we imagine taking f of x and reflecting it, we would get something like that. And our graph that matches our reflection is graph C. Which of the following graphs' inverses would not be a function? Okay, so remember, to test if a current graph is a function, we had the vertical line test. But if I specifically wanted to know if I were to find the inverse of this graph, would its inverse be a function? We had a second test called the horizontal line test. And if something passes the horizontal line test, its inverse will be a function. If it fails the horizontal line test, meaning a horizontal line could pass through more than once, say in graph B, then its inverse would not be a function. So in this case, B is the only one whose inverse would not be a function. Number 8 and 9, these are composition of function problems. So making these a little larger. So we're plugging in, here's g of x, here's h of x, and it wants me to find g of h of 4. And if we're plugging in a value, we're just going to go straight to finding the inner value. What is h of 4? So we're going to go to h, substitute in our value of 4, x cubed minus 1. 4 cubed is 64, and 64 minus 1 is 63. So we now know that the inside here, this function, turns into 63, or evaluates to 63. So now I need to find what is g of 63. We're finding the outer function now, g of 63. So we go to g, which is the square root of x. We plug in 63, and I can see my answer here. Yes, that does simplify, but it doesn't look like any of the answer choices have our simplified version. So 8 is D. Number 9, again, another composition of functions. So let's start from the inside here. Let's figure out what g of 3 is. So we go to g, which is x squared minus 2, 3 squared minus 2, which is 9 minus 2, it's a terrible 9, which is 7. So again, the inside function here evaluates to 7. Let's find f of 7. So plugging in 7, we go to f, which is negative 2x, negative 2 times 7 plus 7. So this gives me negative 14 plus 7, or negative 7. So overall, our function evaluates to negative 7a. Number 10 is another composition of functions. This open dot means composition. And if you're reading this out loud, f of g of x, we can actually write it in the notation we used in the previous problems. F of g of x. And in this case, we're not plugging in a number. We're going to plug the whole expression g of x into f of x. Right, g of x is inside of f of x. So we're going to take this expression, and in f of x, everywhere we see x, in this case just the one place, we're going to replace that x with parentheses and our expression from g of x. So here's our original f of x, and if I replace x with some parentheses, we're going to substitute in g of x, 3x plus 5. And all we need to do is simplify this, distribute our 2 to both terms here. That gives me 6x plus 10. And combining 10 and negative 1, we get 9. 6x plus 9, or C for number 10. Number 11, it's talking about conjugates. So remember, we had conjugates, things like a plus b and a minus b. Those were conjugates we got from difference of squares. Or we had the complex conjugate roots from polynomials, a plus bi and a minus bi, right? Those were conjugates. So it gives me this complex expression, and it wants to know what its conjugate is. So remember, the only difference between them is the sign between the terms. That's it. So this is negative 3x minus I. Negative 3x minus I is our conjugate. For number 12, we're simplifying a radical expression. We could rationalize the denominator. So multiply top and bottom by square root of 2. That would give me square root of negative 100 over the square root of 4, which simplifies to 2. Now in the top, square root of a negative number, we're going to have an I come out for the square root of negative 1. And the square root of 100 would be 10. So the top simplifies to 10i over 2. And simplifying the 10 over 2, we end up with 5i. 13. What is the product of 5 plus the square root of negative 36 and 1 minus the square root of negative 49 expressed in simplest a plus bi form? There's a little extra a in there. Well, let's go ahead and simplify some of these radicals. Because there's a negative sign in my square root, I know we're getting an I out of here, and square root of 36 is 6. So this expression could also be written as 5 plus 6i. Similarly over here, this radical simplifies to 7i. So this expression can be written as 1 minus 7i. And it wants me to find the product of these two, meaning multiply them together. So you can multiply them in any way you'd like. You could use the box method. You could, whatever you feel comfortable with. I'm going to do 5 plus 6i. Go ahead and do the box method here. And 1 minus 7i. So everything in this row is multiplied by 1. So that's 5 and 6i. That's pretty easy. And everything in this row is multiplied by negative 7i. So negative 35i and negative 42i squared. Now remember, I squared is equal to negative 1, and we'll go over why that is again in the next question. But hopefully you have that memorized. We did use that a bunch throughout the year. So if we replace that I squared with negative 1, this becomes positive 42. We get a nice whole number, or a real number. So when we go to combine our reals, 5 and 42, we get 47. And then when we combine our two imaginaries here, we get negative 29i. 47 minus 29i is the product there. Okay, lots of good parts in that question. 14, the expression I to the 10th is equivalent to blank. So remember we did this little chart that we had from our complex plane. We had positive 1 on the right and negative 1 on the left, like our normal x-axis, but this is the real numbers. And going up, we had positive 1i, and down below, negative 1i. This was our complex axis, or imaginary axis. And we said you always started on the positive x-axis, and you rotate counterclockwise every time we do a power of I. So for instance, I to the first is I. I to the second power is negative 1, confirming what we learned further back there. I to the third power is negative I, and I to the fourth power is 1. And then I to the fifth, we just keep going back around this circle. So could I just count out 10 90-degree rotations? Yes, and that wouldn't take forever. However, if they give you a bigger number, remember we learned a strategy where we said because this repeats itself after every 4, that if I take my exponent and divide it by 4, we'd say 4 goes in there twice, which means we go around essentially 2 times, and there would be 2 left over. So we'd go around this whole thing twice, once, twice, and 2 left over means 2 more 90-degree rotations. So we end up at negative 1. This remainder basically tells me how many rotations I need to go after we've gone around this many times, right? And I'm more interested in that remainder to help me get my answer. 15. This expression, hopefully remember, x minus 4 times x minus 4 is just times itself twice, and this is just foiling out. If you go ahead and multiply that out and combine like terms, you should get x squared minus 8x plus 16. The fast way to do these, of course, it's kind of the opposite of factoring. These two multiply to the last term, and they add up to the middle term. So there's your quick way if you're trying to figure out how to come up with those answers a little faster. But C is the correct expression. 16. If one factor of this quadratic is 3x minus 2, the other factor is blank. Well, let's think about this. I have two numbers that need to, or two factors, that if I were to multiply them together, should give me this quadratic. And it told me one of them is 3x minus 2. What is the other factor? Well, if I'm going to get a first term of 6x squared, what do I need to multiply 3x by? It's got to be 2x. And if I know that my constants multiply to negative 6, what does my other constant have to be? It's got to be positive 3. This is the very fast way of finding our solution here. Now, could you do polynomial long division and get the answer? Yes. Could you just factor this into your two setups, 6x and x, or 3x and 2x? Yes, and of course, this case, hopefully you know, it's definitely the 3x and 2x, because one of your factors given to you was the 3x. And guessed and checked your way through there? Absolutely. Okay, 17. What are the solutions to this quadratic equation? And if you take a quick peek at all of the answer choices, they're all positive or negative whole numbers. That means that not only is this factorable, but hopefully very easily factorable. Now, because we want to factor and use zero product property, remember you want to set this equal to 0. And I want to keep x squared positive. So minus 16 equals 0. So we're looking for two numbers that factor or multiply to negative 16 and add up to positive 6, which would be positive 8 and negative 2. Those are the two factors. Then we use the zero product property and get negative 8 and positive 2. Okay, 18. Which of the following quadratic equations is solved correctly? So great, I might have to check all four of these. Let's see, it looks like they took a quadratic equal to 0, they factored it, and used zero product properties. So let's check their work. Do their two factors multiply to negative 35? Yep. Do their two factors add up to negative 2? Yeah. Okay, so I think they factored correctly. And when they set each of these equal to the 0, they got positive 7 and negative 5. I'm pretty sure A is correct. So if we check the other ones, these two factors do not multiply to negative 18. Okay, these two numbers don't add up to negative 9. So both of those were factored incorrectly. And B, when they used zero product property, they didn't change their signs. That should have been negative 1 and negative 6. So only A was done correctly. 19, which quantity should be added to both sides to complete the square? So if you remember completing the square, we move that constant, in this case the 5, to the other side, which was already done. And then we set up a blank on each side. And to complete our square, we needed half of the middle term, half of b, which in this case is negative 8, squared. So half of negative 8 is negative 4, and negative 4 squared is 16. We would need to add 16 to both sides to complete our square. And of course, this would factor as x minus 4 squared equals 21, and you don't have to do any of this. The answer was 16. But then you could square root both sides, and x minus 4 equals plus or minus the square root of 21. Add 4 over, and you get x equals 4 plus or minus the square root of 21. And that would be your solution to that quadratic. Okay. Now, the only reason I'm going over that is our next problem, it's probably a prime candidate to do completing the square rather than quadratic formula. Okay, looking at our four answers, one of them tells me maybe it's factorable, but the rest of them either have imaginaries or radicals with imaginaries, not factorable. So maybe completing the square would be a little faster than quadratic formula. My a value is 1, and my b value is even, meaning it would be easy to cut in half when we square it, like in the previous problem. So in this case, completing the square actually is faster than quadratic formula. So that's the method I'm going to do. You can use quadratic formula if you like, but I'm going to move my constant to the other side and set up a blank on each side. So remember, I need half of b, the value that goes in here, half of b squared. So half of 4 squared is 2 squared, or 4. In fact, we need to add 4 to both sides to complete our square. And this side, the perfect square we just created is x plus 2 times itself twice. On our other side, we get negative 49. To get rid of our square, we can square root both sides. Okay, don't forget to put plus or minus. And square root of negative 49 is 7i. Lastly, I would need to move our 2 to the opposite side. And we get negative 2 plus and minus 7i, which ends up matching with answer A. 21, what are the zeros of this? And if you look at the 4 answers, they even look like quadratic formula. So don't waste your time trying to factor or completing the square. They all have radicals and or fractions. Just go quadratic formula. So remember, x is equal to opposite b plus or minus the square root of b squared minus 4ac all over 2a. So I want to make sure my quadratic is set equal to 0. And then we can identify a, b, and c. In this case, a is 1, b is 7, and c is 5. All nice positive values. So let's substitute in the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Simplifying in the radical, 7 squared is 49. Negative 4 times 1 times 5 is negative 20. All over 2. 2 times 1. Square root of 49 minus 20 is square root of 29. And I don't believe that radical reduces, so I don't think we can go any further. And there it is, answer D. Negative 7 plus or minus the square root of 29 all over 2. 22, which for some reason has gigantic graphs, which of the following represents this equation? So we can even build on what we learned later in the year in polynomials. A negative leading coefficient tells me the right side is going down. I know the right-hand side of my graph is going down. So one, knowing that this is a parabola, tells me it's an upside-down parabola. You can also think of this as a negative a value, so we've had a reflection. And remember that the constant, when it's in standard form, is our y-intercept. Right, if I plug in 0 for x, this term would become 0, and we'd be left with 2. So 0, 2 is the y-intercept of this graph. So I'm looking for an upside-down parabola, definitely not A or C, that has a y-intercept of positive 2. So B is our guy for number 22. All right, 23, it's asking, what are the real roots of this function? Remember that roots is synonymous with zeros, and if they're real, we'll see them on our graph as x-intercepts. So in this case, knowing that roots or zeros is where my graph would cross the x-axis, if they're real, if they're imaginary, I won't see them on this, but we end up, it's crossing at negative 1 and positive 3. So our roots are negative 1 and positive 3. 24. Does this parabola contain a maximum or minimum point? What is the maximum or minimum value of y? So they've given me a quadratic parabola here in standard form. Sorry, not standard form, vertex form. So in this form with A, H, and K. So in this case, my vertex will be located at HK. And for this graph, that is at 4, 1. Remember, H is the opposite of what it looks like. Our A value here is negative 2, which means we have a reflected or upside down parabola, and it's been vertically stretched by a factor of 2. But more importantly, it's upside down and its vertex is at 4, 1. So is this point a maximum or minimum? Well, it's clearly a highest point, so it's a maximum. And it even helps me out. What is the maximum or minimum value of y? Right? X is not maxing out here, it's y. So the highest y value, the maximum y value we get to is 1. So D for 24. Pedro throws a ball up at a rate of 20 meters per second from an initial height of 2 meters. The height of the ball above the ground can be approximated by this function, where t represents the amount of time in seconds since the ball has been released. What is the maximum height that the ball reaches? Okay, well, here we have a quadratic, right? So we have a parabola. Negative leading coefficient means it's upside down. So we have some upside down parabola, right? And we want to find its maximum height, where height is the y value here, right? Y is our height and x is our time. So we can even think of this as drawing in some axes here, that x is our time, which was measured in seconds, and y is our height, which is measured in meters. Okay, and it even starts 2 meters off the ground, right? So we're trying to find what is the highest point here, our biggest height, or the y-coordinate of our vertex. So this would be x is the time, and y is the height. So how do I find vertex if it's not in vertex form? We had a formula for that. And the x-coordinate of the vertex was given by opposite of b over 2a. It's part of quadratic formula. And to find the y-coordinate, we'd plug in x, or in this case, t for time. But let's use this to find the time it reaches its maximum height, and then plug in to find that height. So opposite of b, which would be negative 20 over 2 times a, which is negative 5. So we get negative 20 over negative 10, which simplifies to positive 2. After 2 seconds, it reaches the maximum height. But now we need to figure out what that height is. Now remember, from our formula here, I can generate the height for any point in time by plugging in for t. So to generate our height, we're going to go to the original equation, and everywhere there's t, we're going to substitute in our given time of 2 seconds. So remember, order of operations, exponents first, and then we can go through and multiply and add. So this becomes negative 20 plus 40 plus 2, which ends up giving us 22 meters. So after 2 seconds, it reaches its maximum height, and that maximum height is 22 meters high. Now, could you also graph this and just look for the vertex, the y-coordinate specifically? Yeah, probably. But algebraically, this is how we find our vertex. 26, kind of a funky question. All of these equations are parabolas. Which of the following is basically the correct parabola for this table? And so here's where we're going to kind of outsmart some of the test makers. Usually this point will work in a couple of them. Maybe even that point works in a couple of them. Maybe even that works in a couple of them. I usually say don't pick the very first or very last point. Pick something in the middle. And I usually like picking like the second to last. That point will probably only work on the correct equation. So what we're going to do is we're going to plug in 2 for t and see if we get back an answer of 12. So I'm going to try a here. I'm going to plug in 2 for t and see if we get back 12. Nope, that's not going to give me back 12. So let's try b. Let's plug in 2 for t and see if we get back 12. 4 plus 4 minus 1, that's definitely not 12. Let's try another one. 2 squared minus 2 times 2 plus 1. Well, this is 4 minus 4, 0, plus 1. That's not 12. Well, let's try this one. So again, we plug in 2. 2 squared is 4. 3 times 2 is 6. 10 and 2 makes 12. D is the correct parabola that would give us that table of values. 27. Now we are solving a system of equations. And remember, the solution to a set or system of equations is the x and y pair, or the x, y, and z, the ordered triple pair, that makes all equations true. So this one is actually set up for our elimination method. And remember, in this method, we added the equations together in such a way that either x or y canceled out, right? We wanted to eliminate one of the variables. And right now, if we add these together, my positive 1y and negative 1y, my y's will cancel. So 1x plus 1x gives us 2x. The y's would cancel. And 7 plus 3, don't forget to add those, gives you 10. Dividing by 2 gives me the x-coordinate of my solution. X is 5. In fact, only one of them has 5 as the correct solution. Now, if multiple of them did, we would substitute in. Here I'm using the top equation, plugging in x, subtract 5 from both sides, and we get y is 2. We can also double check that if we plug in this equation, 5 and 2, 5 minus 2 would equal 3. So it does make both equations true. What is a solution for this system of equations? Well, this one, it's not necessarily set up for elimination. Now we could move some stuff around and make that happen. Or we could do substitution, which is I think what they're trying to push on us here. So just to go over a different method. Now, by the way, if you wanted to move this x to the other side and put it in front and line up your x's and y's, I think your y's cancel out right away. So not a terrible method. But let's go ahead and do substitution. It's telling me y is equal to this expression minus the question mark. So that means anywhere I see y, like in this first equation, x minus y equals 2, we can substitute in the expression 2x minus 4. So we're substituting that expression in, distribute the negative sign, combine our x's here, gives me negative 1x plus 4 equals 2. Subtract 4 over, gives me negative 2, and dividing by negative 1, we get that x should equal positive 2. And only one of them has the correct x coordinate of 2. We could check by plugging in. This would probably be a prime candidate for plugging in. 2 times 2 is 4, and 4 minus 4 is 0. Yep, there's our matching y coordinate. And you could even check those answers over here. Of course, 2 minus 0 does equal 2, right? 2 equals 2. All right, so 2 and 0 are the two values that make both equations true. 29 and 30 are system of equations word problems. A cellular telephone company has two plans. Plan A charges $11 a month and 21 cents per minute. Plan B charges $20 a month and 10 cents per minute. After how much time to the nearest minute will the cost of Plan A equal the cost of Plan B? Wow, lots of stuff to come up with there. So one, let's talk about finding the cost of each of these plans for 1 month. So let's do the cost for 1 month. And let's do Plan A in a second here. Let's define our the one thing that will change. So it sounds like this $11 and $20 is like a flat fee I have to pay, and then 21 cents per minute. So let's let X represent the number of minutes, okay, that we're talking, I'm assuming, on the phone per month. And so let's come up with some equations for the cost of Plan A. We'll do that first. So we're going to do cost, I'm just using C rather than F, as a function of X, meaning we put in X the number of minutes, and this will generate our cost. So for Plan A, it's $11 a month plus 21 cents per minute, 0.21x. So for any number of minutes, this should give me the cost if I have Plan A. Let's also do the cost of Plan B. So cost here as a function of the number of minutes x. For B, it's $20 flat fee plus 10 cents per minute. Okay, so we've come up with two equations that represent the cost for the number of minutes. I guess I'll do that in green. Now I want to know, when will the cost of Plan A equal the cost of Plan B? When are these equal? Well, to find out what value of x makes them equal, let's set them equal and solve. When does 11 plus 0.21x equal 20 plus 0.1x? Right, I'm just getting rid of the extra zeros here we don't need. Well, let's get our x's on one side of the equation. I'm going to subtract 10 cents here, minus 0.1. I guess I'll add the 0 in just to line those back up. And let's go ahead and move the constant 11 to the other side. Okay, get our x's on one side, get the numbers on the other. This tells me there was an 11 cents difference and a $9 difference between our plans. So if we divide both sides by 0.11, definitely need a calculator here, this actually gives you 81.818181 repeating minutes. Okay, so we're not talking 81 hours, but minutes. And 81 minutes is pretty much 82 minutes. 60 minutes an hour, that's an hour and 22 minutes. So at an hour and 22 minutes, if you talk that much on the phone during the month, it doesn't matter which plan you go with, they'll cost you the same. However, if you talk more than that, you'd probably want the plan that's cheaper per minute. And if you talked less than that, you'd probably want the one that just has a smaller upfront flat fee, right? So those are some decisions that people used to have to make. Now no one talks on the phone and you guys just text each other anyway. Okay, for 30, this is more like ones that we saw earlier in the year. Jack bought 3 slices of cheese pizza and 4 slices of mushroom pizza for a total cost of $12.50. Grace bought 3 slices of cheese pizza and 2 slices of mushroom for a total of $8.50. What is the cost of 1 slice of mushroom pizza? Well, it's important to know that we do have 2 unknowns here. Let's use, we got what, cheese and mushrooms? Let's use C and M. You know what, let's use some context ones. Let's let C represent the cost of 1 slice of cheese pizza. And let's let M represent the cost of 1 slice of mushroom pizza. Okay, so we have 2 unknowns, even though we only want to come up with the cost of a slice of mushroom pizza. So we still need to solve for these 2 unknowns, and 2 unknowns means we need 2 equations. We need a 2x2 system. And I think from the information they've given me, we can come up with an equation for Jack and an equation for Grace. So let's come up with Jack's transaction here. 3 slices of cheese pizza. So he paid 3 times the cost of 1 slice of cheese, because he got 3 of them. And 4 slices of mushroom. So 4 times the cost of 1 slice of mushroom. And altogether, his bill came to $12.50. Likewise, Grace bought 3 slices of cheese pizza and 2 slices of mushroom, and she paid $8.50. And so here is our system of equations. Now, if I'm doing elimination by hand here and I want to solve for M, I'd like to eliminate C, right? Get rid of the cheese. So I could make these cancel out if I say multiply the bottom equation by -1, which actually just makes all of our values negative, and then we could add them together. We could cancel out the cost of cheese pizza. We end up getting positive 2M, and that equals $4 when we subtract, add 12 and -8, and we end up with M equals 2. It's $2 for 1 slice of mushroom pizza. Okay, we'll continue this next time. Hopefully our live sessions won't have any extra interference.